how I write. So here we are. That's me. I'm in 333 in the Grove. My email you've already got because I've sent you emails out, so you've already got that. Recommended texts. The recommended texts are described on Blackboard. So this book by McMurray is probably the world's standard organic chemistry textbook. And because it's the world's standard, there are a lot of editions. The new edition is expensive. But you don't need the new edition. I can't remember how much a hardbound copy might be, maybe 120 quid. It's a lot of money, maybe 80 quid. That's a lot of money, you know. 20 quid is a lot of money to me. You'll be able to get cheap versions of this on second-hand bookshops online. Abbey Bookshops is one. Amazon might do it as well if you're happy with supporting Amazon and all that sort of stuff. And any edition. I use the 6th and the 4th. I have a number of editions, a couple in the office, a couple in the kitchen. I'm going to pass it around. It's a nice book. It's got a lot of examples. It's got a lot of diagrams. Some things it does very well. The organic chemistry it does really very well. The physical chemistry in it doesn't do quite so well, I don't think. But it's easy to read, and it's what I'm going to base the bulk of the course on. So I'm going to pass it around. I generally wouldn't buy a book unless I'd looked at it and made sure I was happy about it. The library will have copies of the new edition and the work book that goes with it, and previous editions as well. There should be plenty in the library. So I'll pass that one around. It's a very nice book, and I think it will do you for your organic chemistry throughout your degree. There's another book. The details of these books are on Blackboard, so I'm not writing them here. There's another book which is Practical Skills in Chemistry. And you probably have recommended to you Practical Skills in Biochemistry or some other subject, and that might be just as good, but I'm a chemist, so this is the one I've looked at. It's got a lot of information about chemical processes and chemical experiments and that sort of thing. So that third of it is probably deals with chemistry. Third of it, that section of it deals with chemistry. But this last bit is really interesting for degrees nowadays. This stuff would not be in anything that I used when I was at university, but this bit here is about exam technique, how to work with people, how to present a poster, how to write projects, how to write lab books, how to deal with statistics, online resources, taking notes, learning effectively, assignments and exams, giving a spoken presentation, scientific writing, etc. Right, so again, there should be copies in the library. This is a third edition I've got here. I haven't read the first or second editions, so I don't know if they're any good or not. I would imagine that there are, but I don't know. But this is probably about 40 quid. To me 40 quid's quite a lot for a book if you can get it from the library. And also if you can get the second edition for about a tenner maybe, I don't know. One of the things you might do with the people that you're working with is, as a first stage share, agree to one person buy one book and one person buy another. Anyway, it's up to you. But it's a good introduction to practical skills. It's not exactly the way I would do things, but it's not bad. So I'll start that one here. Just have a look at them. So that's a recommended texts. Right, let's see what we're going to look at. So organic chemistry. If we wanted a definition of organic chemistry, we could do worse than simply the chemistry compounds of carbon. this idea that there's distinct types of chemistry, in fact 2 distinct types of chemistry, inorganic chemistry and organic chemistry, come from the days when people believed, a couple of hundred years ago, people believed that there was 2 types of compounds in the world. People believed that inorganic compounds came from minerals and organic compounds came from living creatures. And to make an organic compound, you had to have the spark of life. So that thing that Dr. Frankenstein was looking for, people believed existed in all things that was living, and it was the fact that they had that spark of life, that vitality, was a vitality theory, vitalism, is why organic living creatures could create organic chemistry. Needless to say, that's not the case. And really, not the first, but it's a really major indication of the fact that vitalism wasn't correct. German chemist Wohler accidentally, there's a lot of accidents in science. So he accidentally synthesized urea. And urea was thought to be a compound that only living organisms could make. And I'll tell you what he said. It gives you some idea of where they used to get their chemicals from in that days. He wrote, when Wohler had done this, he wrote to one of the great scientists of the time called Berzelius. And he wrote to Berzelius and he said, "I must tell you that I can make urea without the use of kidneys, either man or dog." So if you think about that, it tells you where his major source of urea, up until the point he made it synthetically, was. And it was a first important step in refuting vitalism. Well, an important step in refuting vitalism. So it's a refutation of vitalism. But this idea of organic and inorganic chemistry is very, very convenient. Your major interests will be the chemistry of living organisms, and incidentally, most of our lab organic chemicals are derived from oil and gas, and therefore are also actually organic in origin originally. But if you look at interstellar space, you can find the synthesis of organic compounds without any life involved in it, of course. And in the laboratory, you could start off with hydrogen and carbon, oxygen and nitrogen, and you could make any organic compound that you wanted, really. But now that we don't believe in vitalism, what's special about the chemistry of carbon compounds that makes them so unique? So carbon as an element is special. And it's special because we get carbon bonds. And those carbon-carbon bonds can be single, double, or triple. So I'm going to ask the people who did PMC 100 why carbon, how can you explain why carbon gives you these double and triple bonds? Before I ask see if I get an answer. I'm just going to say to the people who didn't do PMC 100 should not be alarmed at the fact that I will refer to it occasionally. All I'm doing in that is encouraging students to bring information from modules together. Right? This is a standalone module, you don't need PMC 100 for it. But it is useful, as I said early on, to bring information together from all of your modules. So if I knew anything else I could taught any other module, I would try and do the same thing. It just so happens that I know what was taught in PMC 100 because I hear it. So, any offers for what property, what feature of the periodic table would explain the double and triple bonds? Second row anomaly, thank you very much. For those who aren't familiar with that, the second row elements are a little bit peculiar because they are small, and that allows pi bonding to be efficient. So we get all of these bonds, and then we get chains, we get rings, we get branches of the chain, and then once we've got the chains, rings and branches, and so far we've just talked about the carbon bit, and to these chains and branches we can add hydrogen, oxygen, nitrogen, they're the most common, sulfur, phosphorus, fluorine, the halogens are probably the next most common group. So we can create, I don't use the word very often, a vast number of compounds based on essentially a carbon skeleton. So let's have a look to see what the let's have a look at the structure of the course. You've got it in the sense that you have the but never mind. You get the idea. This is in the syllabus, but the structure is going to look something like that. Something like this. So we're going to look at structure and bonding first. Structure and bonding first. Then we're going to talk about representing structures, how we draw them. Then we're going to talk about stereochemistry. And we're going to talk about two types of stereochemistry. The first one's going to be conformations. So we're going to look at conformations of alkanes and cycloalkanes. And we're also going to look at optical activity. Chirality. Then we're going to look at the mechanisms of reactions in a general way. Then we're going to look at some chemistries, but not the major chemistry will be in the major sort of chemistry, as in what do these type of compounds do, how do they react, will be in PMC 103 for functional groups. But before that, we're going to look at chemistry of alkanes. We'll have a look at the chemistry of alkenes. Quite a lot of chemistry of alkenes. We might mention the chemistry of alkynes, but it will just be a little mention. I've never yet managed to find the space in the module to get anything useful in there. Then we want to talk about the chemistry of benzene. And we're going to talk about aromaticity, this idea that aromatic compounds we wouldn't talk about. And then in the practical, should have started that. Here, you're going to carry out an aromatic titration. And then, so that's going to be the first practical. And then the week, your second practical, you will finish any of that, like I haven't finished, and then you'll go on and do an extraction. You're going to look at an extraction by chromatography of porphyrins. And carotenes from leaves. So this is chromatography. And that practical's in there because chromatography is a really important technique that I'm not sure you will meet in terms of immediate hands-on experience, except in that practical. You might, anybody who's PMC 1 and 2 might meet it there. So it's a chance for you to do some chromatography. It's a very pretty experiment. If you like pretty colours anyway, I like pretty colours. But the porphyrins tie into the module substance because they are aromatic compounds, and the carotenes tie in to the module because they are conjugated alkenes. So they fit in, and these obviously have a significant biological role. And then for the in-course assessment, this is going to be a few typical exam type questions. So that's the outline of what we're going to do in the course. So we're going to start with structure and bonding. If you look at the course synopsis, it'll have these broken down into smaller units of thought. That's the overall. And then this module will form the background to move on in PMC 103 to study the reactions of functional groups. So if we have a look at structure and bonding and carbon compounds. We don't need to say carbon compounds because that's what we're dealing with. So what do we know? Well, just have a look to see. Well, if I asked you to draw the structure of methane, the simplest organic compound you would probably draw it like that. The tetrahedral arrangement of hydrogens around the carbon with a line joining them. And you would use a wedge to tell me that the hydrogen here is sticking out from the board in your diagram. We'll talk about this later on when we're talking about how to draw them. And the dash would tell me and you that that hydrogen is behind the board, and the lines, solid lines, tell you that that hydrogen, carbon and hydrogen are in the plane of the board. And then you would draw, if I asked you to draw ethene, you would draw this, I imagine. It's a flat molecule. All of those atoms are in the same plane. And you would probably draw like this. And you would, I imagine, probably tell me that this single line represents a single bond, these two lines represent a double bond, and these three lines represent a triple bond. But without at first worrying about the nature of the bonding, how do we rationalise the structures? Experimentally, we know that these are the structures of these molecules. We can measure them experimentally by a variety of techniques. So how do we rationalise this structure and bonding from what we know? How do we rationalise these? Or understand them? How do we rationalise and understand these structures? Where would we start? Well, we'd start as scientists with Schrodinger's equations for the electron around the hydrogen atom, and then electrons around more complex atoms. And that would be our first stop. We would say to ourselves, actually we'd start in a slightly different place. We would say to ourselves, can we calculate, I'm not going to do that for sure in that equation. Can we calculate the Schrödinger equation to give us the wave equations for all the electrons in these structures? Can we do that? And the answer is no. So that's our first shot with one. Right, can we do it? Absolutely from first principles. Let's see what we want to what we want to understand here is how are these electrons, how are the electrons arranged? We know where the nuclei are. How are the electrons arranged in these molecules? Is what we would want to know. And how is that going to affect their chemical properties? So, for example, we can see here, we've got a double bond, so we might start thinking, well, this is going to be rich in electrons. So this is going to be a place where the molecule can react with rich in electrons. Here, we see all of these four bonds are exactly the same. All the electron distributions look as if they might be the same. So from first principles, we're not going to get where we want to be. So the next step is to say, okay, can we understand it if we accept a model where we build up the structure from the atomic orbitals of the atoms involved. So that's the question. The answer to that question was no. So the next question is, can we build a model and in actual fact, I'm going to call them models because we have a number of them that we use. So can we build a model for these structures using the atomic orbitals that we already know about? And the answer to that is yes. And that's what we'll start the next lecture with. The models that we use, the bonding models that we use to understand these structures. So I'll see you tomorrow.